Hello, my name is Bill Kinney, and this is the 37th video that I'm making in a series on the foundations of arithmetic, algebra, and graphing, with an emphasis on real-life interpretation and application. It's part 6 of a sub-series on exponents, roots, and logarithms, with an emphasis on calculator usage. The first 4 parts of the sub-series focused on exponents and what they mean. And in the last video, we looked at an application. Financial application: if you get a certificate of deposit that pays 2% interest once per year, which is actually pretty good at the moment in 2012 when I'm making this. It was pretty bad back 20, 30 years ago, and maybe as bad when you're watching this. But anyway, we were wondering how long it would take our money to double, and we saw that the answer was 35 years through some experimentation with a calculator. By the way, before I show you another calculator, how to do this on another calculator, I want to just mention that when you see a problem like this, you should also think in terms of the fact that your money is doubling doesn't mean it's doubling in value. It's only doubling as an actual amount of money, but the value might not double because of inflation. So keep that kind of perspective in your mind when you're thinking about investments. Just because the nominal value of your money is doubling, that doesn't mean the actual real value of your money is doubling because of inflation. The purchasing power goes down. Anyway, let me check this with this calculator. And so ultimately, through some experimentation, we saw that if we take 1.02 and raise it to the 35th power, that's going to be pretty close to 2. On this calculator, to raise to a power, I have to press that button right there, y to the x. So I press it, and then I press 3.5 for 35th power, and then equals, down in the lower right corner, and there you see it's almost 2. If I now multiply that times 1,000, which is what I was pretending my initial amount was, it doubles it almost. Yeah, $1,999.89. A comma there, it looks like. The 1,000 is irrelevant. I could have started with any amount. Because I'm multiplying by a number real close to 2, it's going to double any amount. I hope you took the time to think about why the answer to this next question was this dollar amount. I showed it on the last video kind of quickly. And what I did was I ultimately took $20,000, which is the amount I want to have in the bank after 10 years, and I multiplied it by 1.02 to the negative 10th power. You want to have that much 10 years in the future. What should you put in the bank now? Let me show you this calculation on this calculator. So I'll go ahead and type in 20,000. Let's see, wait a minute. Probably would be better to do something else in this calculator first. I'll do 1.02 to the negative 10th power first. I think I haven't experimented with this, but I think I have to type 10 first, and then there's a negative button down here. Yep, there we go. 1.02 to the negative 10th power equals that. And that's the thing that I actually have to multiply 20,000 by to get the $16,406.97. So if you didn't quite catch that, you might want to rewind and do it again. Why does that work? Well, to go backwards in time, I said essentially you've got to keep dividing by 1.02, and ultimately divide by 1.02 to the 10th to go back in time 10 years to find the present value of this future value of $20,000. Why is that equivalent to multiplying by 1.02 to the negative 10th? The reason, I hope you remember, is because of what negative powers mean. 1.02 to the negative 10th power means 1 divided by 1.02 to the positive 10th power. That's the meaning of that negative power, of that notation. And the calculator is programmed to know that, in a sense. So that's why raised to the negative 10th power, and so you can think of that as an application of negative powers. Here's another question. What interest rate is required for your money to double in 12 years? This is a little tougher question, and I'm probably not going to have time to answer it in this video, but I want to use it to motivate an idea, and that idea is, excuse me, what does it mean to raise a number to a power that is a fraction? I haven't talked about that yet, and so now I'm going to do that. So I'm going to talk about it without reference to the application for a bit in this video, and then probably at the start of the next video, and then hopefully in the next video I'll be able to answer the question. Let's start with an example. So the question is, I want to try to answer here, is what should it mean to raise, for example, 2 to the 1/2 power? You may recall from the first 4 videos or so of this sub-series that I spent some time talking about, what should it mean to raise 2 to the -1 power or 2 to the 0 power. And now I want to see if I can extend the idea of raising to a power to include powers that are rational numbers. And in particular, we'll start with this example. It's probably not clear to you. Maybe you remember, maybe you don't, but how might we try to figure it out? I'll avoid the calculator for the moment. What should this mean? The key thing is to realize that you want the same properties of exponent that we've been talking about to continue to hold. For example, one of those properties was that if you have a number and we raise it to a power, and then you raise the resulting number to another power, that you can get the same answer by raising the original number to the power which is the product of the two powers. B to the m, all raised to the n power, is the same as b to the m times n, and I gave some reasons for that in the case where m and n were positive integers. What does that mean about this? Well, it would mean that, for example, if I squared this number, if I want this to still be true, even if m or n or both are rational numbers, then I would want, I also go ahead and say it as should equal, and in fact will equal, 2 to the power that is 1/2 times 2. 1/2 times 2 is 1. Should equal 2. If I want this property to still work. What does that mean about what this number should be? Think about it. It means that when I square the number, I should get 2. When I square a number, I should get 2. What is that number? It should 2 to the 1/2, therefore should equal, what number has a square equal to 2? Well, what positive number at least? It's the square root of 2, symbolized by that. And that indeed is a definition that we make. We define, in general, a positive number to the 1/2 power to equal the square root of that positive number, the positive square root of that positive number. Well, technically non-negative, we can include 0 here. For any non-negative real number, we can define that number to the 1/2 power to be the positive square root of that number. Why do I say positive square root? Well, there are negative square roots as well. For example, the square root of 4 is 2, and by definition, when I write that symbol, I mean the positive square root. But there is a negative square root as well, but you'd symbolize it this way, it's -2. 2 and -2 both have a square equal to 4. So if you want the negative square root, you'd write that way. And in general, I'll wrap this video up by just saying that for any positive number and for any rational number of this form, where m is a positive integer, you define b to the 1 over m power to be the mth root of b. What does that mean? It means when you raise b to the 1 over m to the mth power, you get b. The positive mth root of b. M here is, again, a positive integer. And we'll continue with this in the next video.